So how to design or size a control valve? Okay, so we will perform one detailed numerical. Okay, if you have any question, any doubt, you can just raise your hand, so I will explain you. So it's a real plant case. Okay, from my previous experience, how I have selected one control valve for my client. So let's start. Okay, so it was a real plant control valve sizing. Okay, so it's a real plant case. Okay, so I have selected control valve for cooling water flow control valve. Am I audible, guys?
Yes.
Okay. So what was the service? Cooling water to cooling water to process heat exchanger. Okay, and it was a flow control valve, FCV. Okay, flow control valve. And you should know the standard. Okay, what standard control valve like you have to select. Okay, so standard basis, as a process design engineer, you should know the codes and standards for everything. Whatever you are going to design, there are certain standards given. So it is IEC 60534. Okay, for liquid. Okay, liquid control valve sizing. Okay, for liquid, I have selected flow control valve. Okay, and the fluid was water. Okay, process design data. So fluid parameter, we have parameter and the value. So it was fluid, it was in liquid form, and fluid was cooling water. You should know the temperature. So it was 25 degrees Celsius. Okay, then normal flow was 40. Sorry, normal flow was 100 m cube per hour. Okay, minimum flow was 40 m cube per hour. Maximum flow 120 m cube per hour. Okay, then specific gravity. Okay, specific gravity of water is 1. Initial pressure, initial, or you can say inlet pressure. Inlet pressure is 10 bar. Outlet pressure is 5 bar. Okay. Design delta P is 5 bar. I will explain you. Okay, what exactly we are doing. So vapor pressure, VP vapor pressure at 25 degrees Celsius is 0.032. Okay, bar absolute. Okay, for water at 25 degrees Celsius, vapor pressure is 0.032. Okay, it's very important. Okay, and we also required the vapor pressure is also required for the pump sizing. Okay, So your interviewer will ask, okay, what data is required for sizing or selecting any pump. So vapor pressure, you should explain the vapor pressure is also required. Upstream pipe, that is 6 inch. Wall type, it's a globe wall. Okay, I will make one video, detailed video, uh, so in which I will explain what are the types of control walls, types, and the other related details about the walls for freshers and beginners. Okay, you can check our official YouTube channel. Okay, in 1 or 2 days, I will prepare that video and I will upload that video. FL, assume, let's say it's 0.90, and XT assumed is 0.70. Okay, so I will explain this. Okay, no worry. What is XL and what is XT? So FL and XT is world time specific manufacturer data. Okay, so this data we got from the manufacturer. We got this data from the manufacturer. Okay, for actual procurement, we replace assume values with the vendor's certified coefficients. Okay, so for now we don't have any vendor data, so I have assumed this. But ultimately, this FL and XT we got from the manufacturer. Okay, so we are not responsible for designing that. Okay, so see, this is a control wall. Let's say this is a control wall. Or I can draw it. This is a control wall. This is the upstream. This is the downstream. Okay. So what our numerical is saying, what is the problem statement? So we have a water, okay, cooling water at 25 at 25 degrees Celsius. Its flow is normal flow is 100 m³ per hour. Okay, and the pressure is 10 bar. Okay, so to control this flow, we require this control wall. Okay, this is a globe FCB. Okay, flow control wall. So initially the pressure was 10 bar, and in the downstream side it is 5 bar. Okay, so what is the pressure drop here? Can you tell me what is the pressure drop here? It is a 6 inch. So simply pressure drop means what pressure is reduced in the control bar. So 10 minus 5 is 5 bar. So total pressure loss is 5 bar inside the control bar. So one more thing, if the pressure is not dropped, so means your control wall is not controlling anything. So in control wall, pressure drop should be there. Okay, always remember one thing, in control wall, if it is like pressure drop is not there, so your wall is not operating. Okay, so normally control wall operates at let's say from 20 to 80% opening. Okay, normal operation is in 20 to 80%, means your control wall. For less flow, your interviewer will definitely ask this question: how will you size the control wall, and what is the minimum and the maximum opening of the control wall? So minimum is 20%, maximum is 80%, and the best efficient operation is 50 to 70% wall opening. Okay, so here your normal operation can take place. Okay, so these are the basic things you should know, and while attending any interview, they will ask you these questions. Okay, so you should know this thing. So step 1, so delta P is 5 bar. Okay, then required CV. Now we are the responsible person, we are the responsible people for calculating the CV. Okay, this is step 2. Okay, required CV. So we required a CV, okay, to size any control wall. For liquid service, you should know this formula. Okay, Q is equals to CV under root of delta P by specific gravity. This is a standard formula. Okay, note down in your notebook. Standard formula, and very very important. Okay, very very important. Okay, so we know Q, we know delta P, we know specific gravity, but we don't know the CV. Okay, so CV is equals to Q under root of Sg divided by delta P. Okay, so this is the arrangement for calculating CV. Okay, you should know this formula. Okay, this is the standard formula for calculating the CV value. Okay, let's put all those values. So CV, Q, what is a Q? So 100, Sg is 1, delta P is 5. Okay, so therefore CV, I have calculated that, so I got it 44.72. Okay, this is how like CV is calculated. Okay, so required CV is 40.72. Okay, then convert step 3, CV to KV. Okay, so there is a standard value of KV, that is 0.88, not 88, it's 865 into CV. Okay, so KV is equals to 0.865 into 44.72. So KV, I have calculated this value, so I got 38.68. Okay, so in my Copilot, we will perform this. Okay, so, I have designed one Copilot, so we will try to solve this numerical. Yes? हाँ?
सर वो जो हमने बार को उसको पास्कल में कन्वर्ट किया था इस कैलकुलेशन के लिए।
नहीं, इसमें पास्कल में नहीं कन्वर्ट करना आपने। नहीं, मैं समझा नहीं क्या बोल रहे हो। नहीं, इसमें नहीं नहीं, इसमें इसमें आपका MKS में ही रहेगा। इसमें SI में नहीं कन्वर्ट करेंगे हम लोग। वो हम लोग कब करते हैं, जब जैसे तुम लाइन साइज और पंप की बात कर रहे हो, बराबर? क्यों अभी इसमें ये चीज़ ठीक है, पॉइंट वैलिड है आपका, बट क्या होता है कि कंट्रोल वॉल्स हमेशा जो मैन्युफैक्चरर्स होते हैं, ओके, क्योंकि पास्कल बहुत छोटा यूनिट है, बराबर? पास्कल इज़ वेरी स्मॉल यूनिट, बट नॉर्मली जो मैन्युफैक्चरर्स जो होते हैं, सो वो हमेशा बार गेज में ही कंट्रोल वॉल डिज़ाइन करते हैं। बार में ही रखेंगे, आप दोनों अप्रोच रख सकते हो, कोई प्रॉब्लम नहीं है। अप्रोच आप रख सकते हो, पास्कल भी यूज़ कर सकते हो। ओके, बट क्या क्या फ़र्क पड़ेगा उसमें? क्योंकि नहीं, इसमें आपका जो फ्लो जो है, ओके, फ्लो एसजी यूनिटलेस है, प्रेशर आपका बार में है, हम लोग कर सकते हैं। ओके, जैसे 5 बार है तो उसको 5 लाख पास्कल में वी कैन, हम लोग कर सकते हैं। डेल्टा भी 5 लाख पास्कल हम लोग रख सकते हैं। बट गेज नहीं, बट गेज प्रेशर को डायरेक्टली एब्सोल्यूट प्रेशर नहीं मान सकते हम लोग, बराबर? अभी आपका वाटर का वेपर प्रेशर भी हमको दिया है, ओके, तो पास्कल एब्सोल्यूट में वो दिया है। नहीं, सीवी यूनिटलेस वैल्यू, सीवी इज यूनिटलेस वैल्यू, सीवी इज कंप्लीटली यूनिटलेस वैल्यू। ओके, हाँ, पॉइंट वैलिड है आपका, बट सीवी जो है, सीवी इज ऑलवेज यूनिटलेस वैल्यू। सीवी इज ऑलवेज यूनिटलेस वैल्यू। क्यों है, मैं बताता हूँ आपको। अब मान लो कि आपका सीवी जो है एक डायमेंशनलेस वॉल फ्लो कोएफिशिएंट है। Okay, dimensionless है flow wall coefficient. Flow wall coefficient, this is a flow wall coefficient. Okay, it is not a dimension. It's not with the dimensions. Okay, it's just a flow wall coefficient. And normally जो data sheet में होता है, so it is like a और CV को हम लोग अगर MQ per hour लिखेंगे नहीं होता है. Okay? So commercially it is a unitless value. Okay, and KV, your KV also dimensionless value. You don't have any dimensions. Unitless value. Okay. Point valid है आपका, but still जो vendor होते हैं, vendor जो होते हैं, manufacturers जो होते हैं, so they don't prefer any dimensions. अगर आप MQ technically MQ per hour आना चाहिए वहाँ पर, but नहीं है, नहीं करते वैसे. It's a industry standard. Technically हम लोग debate कर सकते हैं इस पे, but it's a industry standard and we don't use any units for that. Okay. वैल्यू चेंज हो जाएगा, वैल्यू चेंज हो जाएगा. नहीं, अगर आप मान लो कि अब पास्कल में भी अगर कन्वर्ट कर रहे हो उसको, हम लोग अगर उसको पास्कल में भी अगर कन्वर्ट करेंगे तो सीवी का वैल्यू कितना आएगा हमारा? कहीं बहुत बड़ा डिजिट आएगा, बराबर. हाँ, तो नॉर्मली जो वेंडर डाटा होता है उसमें वो लोग नहीं कन्वर्ट करते. सीवी का वैल्यू हमेशा 2 डिजिट में ही रहता है. ओके, इट्स अ कमर्शियल फैक्टर. ओके, इंडस्ट्री स्टैंडर्ड्स हैं. इंजीनियरिंग में हम लोग कुछ भी कर सकते हैं. इसको मैं 10 तरीके से रिप्रेजेंट कर सकता हूँ, 10 तरीके से हम लोग इसको बना सकते हैं, बट एज पर द इंडस्ट्री स्टैंडर्ड्स हम लोग को वो चीज़ फॉलो करनी पड़ती है. ओके, सो सीवी शुड बी इन डबल डिजिट ऑनली. 3 डिजिट में भी रह सकता है, बट फॉर 6 चेंज के लिए सीवी तुम्हारा 100 तक जा सकता है. ओके, so step wall selection. Okay, so see wall selection, good question. But देखो, let's see. अगर आप देखोगे ना कंट्रोल वाल का डाटा शीट आप देखोगे तो उसमें सीधी आपको ऐसे मिलेगा. हम लोग उसको बहुत बड़ा डिजिट में नहीं करते हैं, स्टैंडर्ड प्रैक्टिस है. सो सपोज the vendor database gives, okay, for 2 inch, let's say it is 25. Okay, ये wall है, this is the wall and this is the rated CV. Okay, for 2 inch, let's say it's 25. For 3 inch, let's say it's 40. 4 inch, let's say it's 58. And for 6 inch, let's say it is 100. Okay, so हमारा कितना आया? So it is like a 44, so it's around 4 inch, right? So we need, see, ये आप लोग को अभी समझ में आ जाएगा तो आगे जाके कंफ्यूजन नहीं होगा. We need CV rated and CV required. Okay, so it should be always greater than the required. Okay, so our required is, so you always select a higher size control valve. So our required CV is 44.72. Okay, so therefore can we use 2 inch? No. Can we use 3 inch? No. Can we use 4 inch? Yes. Okay, because rated should be greater than the required. So our required is 44, and what is the nearest value of 44 is 58. So we cannot select 40, so we need to select 58. Okay, this is the rule. So recommended is this is the recommended. Okay, recommended wall. Okay, next is wall opening. Okay, it's very important, wall opening. And this is our step 5. Okay, so this is extremely important for us. Okay, like what is the what should be the opening of the control wall. Okay, so wall opening is equals to required CV divided by rated CV into 100. Okay, so what is the required? So required was 44.72 and the rated was 58 into 100. Just cross check it. So I got it 77.1%. Okay, so this is the required wall opening and this is the formula. Guys, you note down these formulas. Okay, it's very important. So if you're engineering, what is our engineering rule? Okay, EPC rule while selecting any control wall. So if it is less than 60%, means it's oversized. If it is in the range of 60 to 85%, it's ideal. Okay, and if it is at 85%, so it is undersized. Okay, so your wall should open at 60 to 85, and I told like 50 to 70. Okay, but usually we can use from 20 to 80%. Okay, so this is the ideal. This is the ideal number. Okay, because wall opening is accepted in between 20 to 80%. Got it? This is why this case is nice test case. Okay, now pressure ratio. Step 6, pressure ratio. Okay, so PR P2 by P1. Okay, so in compressor we have to see this. Okay, pressure ratio. So 5 by 10. So it is around half. Half means what? 0.5. Okay, so PR is 0.5. Okay, it is also unitless value. Step 7, absolute pressure conversion. Okay, so that was in gauge. Okay, so P1 absolute. Okay, so 10 plus 1.013. Okay, so it is 11.013 bar absolute. Okay, so absolute and gauge both are different. Okay, so this was P1 and P2, that is 5 plus 1.013. So you will get 6.013 bar absolute. Okay, so this is very important. Okay, conversion from gauge to absolute, it's very important. Step 8, flushing check. Okay, okay, flushing means what? Like generation of vapors. Okay, means when the downstream pressure is at or below vapor pressure. If it is decreasing below vapor pressure, means flushing will occur. Flushing means what? Like vapor can form, boiling can form. So your P2 is less than PV. So here 6.013. Okay, and it is greater than 0.032. Okay, so means no flushing. Okay, what is the vapor pressure of water at 25 degrees Celsius is 0.032. So, and we have this one 6.013. So no flushing. Okay, no flushing is expected. Then choke flow, step 9. Okay, okay, for IEC 60534 screening calculation, we use delta P choked. Choke flow is equals to F square L P1 minus FF and PV. This is a standard formula. Okay, and what is the choke flow? What is a choke flow? So choke flow is what? Like at vena contracta, in any control valve there is a vena contracta. So at this point, this is the vena contracta. Okay, so here what happens? Your pressure at this point, what happens? Your pressure drop down drastically. Okay, pressure drop is more at this point. So if your pressure decreases, means at the same time your velocity increases. Okay, so this is the relation. Okay, P is inversely proportional to velocity. Okay, remember this thing. Okay, in line sizing, in control valve sizing, this is the most important relation. If the pressure is decreases, velocity increases. If the velocity increases, means pressure decreases. Okay, while doing the line sizing, this relation is very important. Okay? At vena contracta, what happens? At this point, your pressure drops drastically and your velocity reaches to sonic velocity. Okay, not supersonic, but it reached to sonic velocity. Okay, at sonic velocity, what happens? There is a choke flow. Choke flow means what? After that, there is no flow. Okay, after this choke flow, there is no flow. That is at that moment, it is like a sonic velocity. Okay, so you should know these things. So calculating the choke flow, there is a standard formula, and you should know this formula. Okay, in interview, they can ask you this question. Okay, what is the choke flow velocity formula? So for water at 25 degrees Celsius, use a representative critical pressure of approx. Okay, so PC is 2 to 1 bar absolute. Okay, this is the standard value. Okay, FF 0.0 0.96 minus 0.28 under root of PV by PC. Okay, these are the standard values. Okay, we don't need to find, or we don't need to calculate these values. Okay, we don't need to obtain these values. This is the standard values and standard formulas. So you will get FF is 0.957. Okay, so FF is 0.957 and FL is, you don't need to obtain these values. Okay, these are the standard values. We don't need to obtain these values. Sometimes ready available references are there in the market. So choke flow 0.90 square 11.013 minus 0.957 into 0.032. Okay, so I got this value P choked. P choked. Okay, so it is 8.9 bar, and our actual is delta P is 5 bar. Okay, so means what? At this point your flow will be choked. Okay, but our delta P is 5 bar, so 8.9. Okay, so is it a choke flow or not? Is it a choke flow? Yes or no? Let's say if it is a 5, let's say if it is a 8.9 and the choke flow value is 8.9, so will it be choke flow or not? Or let's say it's a 9 or 8.9, will it be choke flow? Which one is the no choke flow? This is a no choke flow. Okay, because this is the limit. Okay, this is the limit. Okay, if it is equal to 8.9, so choke flow will be there. If it is a greater than this, again choke, but it is less than 8.9, so it is not a no choke flow. Okay, so if your delta P increases, means there is a choke flow. And as I said, at this point, at this Venn contract type, the pressure drops. Pressure drop means delta P if increases. Let's say if it is a 8 or 8.5, the pressure drops here, means it is like near to the choke flow. Okay, so no more pressure drop is here, and this point is called as a Venn contractor. Okay, step 10, cavitation. Okay, cavitation. Now what is a cavitation? Okay, so cavitation is the form of air bubbles. Okay, cavitation is in pump, cavitation is in control valves. So cavitation is the form of air bubbles. Air bubbles, or you can say if it is like reaching to the vapor pressure of the liquid. Okay, if it is near to the vapor pressure, it is near to the liquid vapor pressure. So it is like the cavitation can be happen over there. Okay, so the standard formula is okay. So the cavitation is equals to P2 absolute minus PV divided by delta P. That is a pressure drop. So 6.013 minus what is the vapor pressure? 0.0. Okay, so 6.013 minus 0.032 divided by 5. Okay, so sigma, so I got this value is 1.196. Okay, so this tells us the wall is operating with a downstream pressure, okay, substantially above vapor pressure. Okay, so it is above the vapor pressure, it is not at or equal to vapor pressure. There is a big difference in the vapor pressure, okay, and the operating pressure. Means what? There is a no cavitation. Okay, okay, when cavitation could occur, like if it is a 0.032, okay, and if it is less than that or equal to 0.032, so cavitation can occur. Okay, if it is equal or less than that, so cavitation can occur, but it is a 1.196, so no cavitation. Okay, then velocity, line velocity, step 11, line velocity check. Velocity is very important. Okay, pressure and velocity, our whole industry is running on that. So let's say, not suppose, but we have selected, we know the upstream line is 6 inch. Okay, so with the approximate internal diameter, so d is equals to 154 mm. Okay, so in meter 0.154 meter. Okay, so flow, we know the flow. Okay, what is the formula? Q is equals to, how to calculate the velocity? Okay, area into velocity. Flow is equals to area into velocity. So we know the flow, we don't know the velocity. Now we have to calculate the area. Okay, for area we know the tube diameter. Okay, so what is the formula for, before that, every flow should be in, it should be in meter cube per seconds. So we have 100 divided by 360, so it is around 0.02778 meter cube per second. Okay, always calculate your flow into meter cube per second. Okay, so area is equals to pi d square by 4. Okay, this is very common and very useful. Okay, for line sizing, for everything. Okay, if you want to calculate the area, so you have to use this formula. So pi, what is the value of pi? 3.146 into what is the diameter? Diameter we have calculated 0.154 meter square and divided by 4. Okay, so you guys try to calculate by yourself also. I have already calculated those values. So I got this area, and you need to cross check it. Okay, sometimes maybe I can make mistakes. Okay, so area, we got the area is 0.0186 meter square. So velocity is what? Velocity, the basic formula is Q is equals to area into velocity. Okay, this is the basic formula for line sizing also. Okay, so we know the Q, we know the area, now velocity. So V is equals to Q by A. So what is the Q? 0.02778 divided by 0.0186. Okay, so V is, I have calculated, so V is 1.49 meter per second. Okay, so velocity you calculated, you got 1.49 meter per second. Okay, so guys, this is for the normal flow. Okay, this was for the normal flow, but I will give you one homework. Okay, so this was for the normal flow, and the Q value was 100 m cube per hour. Okay, so I will give you one homework. Calculate the same, using the same method for the minimum. Okay, what was the minimum flow? It was 40 m cube per hour, and the maximum flow, max flow was 120 m cube per hour. Okay, so this is two values you have to calculate. Okay, so this is how like a control wall CV is calculated. Okay, okay, so any question guys on this? It's a very detailed, if you know this methods, or if you practice all those steps, so maybe you will not face any problem in the future related to this control valve. Okay, so all steps we have already covered. Now let's try to solve this with the AI. Okay, let's calculate. Let's try to solve this problem with the AI. Want to see how to use, how to use AI? Want to see, guys? Yes or no? Am I audible, guys? Okay. So I'm showing you how this AI, not AI, but this coding is used. Okay, I don't show anything with people actually, but you are my student. Okay, I trust you guys, and that's why I'm showing you this thing. Okay, so let's check how to calculate the, the CP value with the Python coding. Some bug issue is there. Warning. Okay, running. Okay, any bug issue, I think. Just hold on. Python. Streamlight run. Okay, maybe some error is there. I need to check what error is there. Okay, some bug issue is there. I need to check. Okay, different program is running over. Okay, no worry, guys. I will show you. Okay, in future, definitely I will show you. Okay, I need to check in my program what is happening over there, and I will keep one more session on that. How to solve numericals with the co-pilots. Okay, and I have shared that in channel also. Okay, so any question, guys, on this control valve? This is how. See, one more thing. There are like a three types of flow. Okay, three type of phases. One is single phase. Second one is double phase or two phase, and third one is gas phase. Okay, so we have discussed the single phase only. Two phase and gas phase having different criteria. It is not same like this. Okay, everywhere for the line sizing, for the control ball sizing, we have this 3 different steps. Okay, so if you want to select a CV for 2-phase or for the gas phase, the criteria and the steps are different. Okay, got it? Any question, guys? Okay, so no question, we can drop the call and see you tomorrow, guys. Good night.